So we basically finished this chapter. So I just wanted to give you some hints for the problems this week. And for the first problem, you're doing some dimensional analysis, but you need to calculate dimensions of bras and kits. So I just wanted to discuss a few things about that. So first of all, just some comments on notation. So when I use the square bracket, this is meant to stand for the dimensions of whatever is inside that square bracket. So this would be the dimensions of area, and we know that that is length squared. So this is just a statement about my notation. I would like to know what is the dimension of ket x and what is the dimension of bra x. Now, how do we think about kets and bras? Well, one way to think about it is the ket is a column vector and the bra is a row vector. So you get from the ket to the bra by taking a transpose and by taking a complex conjugate. The transpose doesn't change dimensions. The complex conjugate doesn't change dimensions. So whatever the dimension of the ket is, it will be equal to the dimension of the bra. To understand what these dimensions are, recall that if we take the bracket between bra x prime and ket x, this is equal to delta of x minus x prime. So if we knew the dimensions of the delta function, we would immediately be done. So our problem has become now, how do we work out the dimensions of the delta function? Okay, so to do that, well, I'm going to write down an integral. So let's take the integral dx, and let's just integrate delta of x. And I'm going to integrate from a to b. And I'm going to make the assumption that a is less than naught and b is greater than naught. In that case, my integration domain includes the point where the delta function is satisfied, so you know that this integral is just equal to 1. Now, what's the use of doing this? Well, I know that 1 is dimensionless, so this is length to the naught. On the left-hand side of the equation, I know that dx itself is a length. So a length times the delta function has to be dimensionless. That's what this equation tells me. And I immediately learn that the delta function itself must have a dimension of length to the minus 1. And this argument can be applied for any delta function. And the conclusion is always the same. Delta of x is 1 over the dimension of whatever sits in its argument. Okay? So delta of x is length to the minus 1. If you had a delta function of energy, some energy sitting here, the dimensions of this would be energy to the minus 1. So that's I hope the general rule is clear now. Now, since delta of x is length to the minus 1, it means that bra x prime must have dimension of length to the minus 1, and ket x has dimension of length to the, bra x prime has dimensions of length to the minus 1/2, ket x has dimensions of length to the minus 1/2, so their product would have dimensions of length to the minus 1. So in this way, we learn that the dimension of the bra equals the dimension of the ket equals length to the minus 1/2. And when you're working out the dimensions of any bra or ket, the logic is always the same. For the second problem in the homework, I've simply asked you to go through part of the integral that we did in class. And then for the next problem, I've asked you to carry out the approximation, the approximate evaluation of the integral over P for our probability amplitude. Now, that method goes under the name of the stationary phase approximation. And they are closely related. approximations called the saddle point approximation and steepest descent. These are extremely important methods. I want to give you some conceptual understanding of what you do when you're doing stationary phase approximation. So let's imagine I ask you to calculate the integral of some function f of x. So I want you to calculate the integral of f of x dx. And let me tell you what f of x looks like. Let's invent a nice f of x. So f of x does something like this. Now, if I ask you, what is the integral of that f of x, you're going to tell me, well, it's going to be either exactly 0 or close to 0. And the reason why you'd make that guess is that you catch the same amount of area above the curve as you do below the curve. You know, integrating a sine wave or a cos wave over one period just gives you naught for precisely that reason. You catch the same amount of area above the curve as you do below the curve. But now let's imagine for some reason our function f stays constant for a little while and then it starts to wiggle as it was wiggling before. Okay. Well, if you look at this, you would say this region contributes nothing. You'd say this region contributes nothing. So the important region is this region in the middle. That's where all of the contribution is coming from. So this is the important region. Now, what stationary phase approximation does, it approximates your function by something simpler, but such that you very accurately reproduce how f of x behaves in this region where most of the contribution to the integral comes. So if you were doing this integral and you're meant to get 1 from this region, maybe stationary phase would give you 0.99. So very accurate in this region that I've circled in yellow. And from these red regions, stationary phase would not be very accurate. It's not built to be accurate there. So maybe from the red regions, well, you don't quite get a contribution of naught. Maybe you get 10 to the minus 18. And stationary phase might get that completely wrong. It might give you 10 to the minus 20. But who cares? All of the contribution to the integral is coming from the yellow region. So that's all you need to get right. And that's what stationary phase does. It gets that yellow region right. Now, why is this called stationary phase? Well, you might have imagined that f of x, so actually let's imagine here that we were plotting the real part of f of x, and that f of x looks like something like e to the I phi of x, something like this. So phi of x we would call the phase of the function. And this yellow region over here, this is where the phase stops changing. So it's where the phase is stationary. So that's the idea. You're going to approximate the function so that you get a very good description of it in the region where the phase is stationary. And so you get a very accurate description of the region that contributes the most to the integral. Now, there's a very related approximation that you would apply, not when your function is wiggling a lot. Maybe your function doesn't wiggle at all, but it looks something like this, okay? This is x. Here is f of x, and the function does something like this. It goes up and it comes down. Now, if I say to you, well, where does the contribution to the function come from? Well, you'd say, again, this is the important region, in this region over here. And if we decided to write f of x now as e to the phi of x, so very similar to the previous way we wrote our function, the only difference is previously we had an I multiplying the phi. Here we don't have an I. So this function is real, okay? Then how do we characterize this point over here, which is sort of in the middle of the important region? Well, when we're going up here and the function's increasing in size, phi of x is getting bigger, bigger, bigger. And then we hit the maximum, phi stops changing, okay? So at the top here, you could put a tangent. The function stops changing, so phi stops changing, and then you start coming down again. So both yellow points, in both the case that the function was wiggling very severely, and in the case where the function just peaks somewhere and it's zero outside of there, both of these regions are characterized by the fact that our function phi of x, so which was a phase in the previous example, and here it's really setting the amplitude, phi of x is stationary. Okay, so it would be exactly the same idea. You approximate things accurately inside the yellow region, and outside, where not much contribution to the integral is coming, you don't care if your approximation is very accurate or not. These methods are all collected together into the very general method of steepest descent. Okay, so I want you to look on the internet for steepest descent. I want you to look for stationary phase approximation, and I want you to look for the saddle point approximation. These are all related methods. You should study these three techniques together, and they are enormously helpful. If you've seen tables of special functions like Bessel functions or hypergeometric functions, where people state what their asymptotic behavior is, you might wonder how they knew that these special functions have that asymptotic behavior. Well, what they did is they wrote down an integral representation for the special function, and then they applied these approximation techniques. And that gave them what you will read in the tables. So these are extremely useful techniques. You can use them very often to estimate the size of an integral that you can't evaluate exactly. And they also help you with asymptotic analysis. So very good thing to master. So good luck with your homework. Do the best that you can and try to master these enormously useful techniques.